talk just a little bit about something called in-behavior models, something that is in our textbook, which I had not covered. So what is an in-behavior model? So I want to show you an example. We're going to find an in-behavior model for this function f of x, which I have this rational function here. So to find the right in-behavior model, you're going to think about what happens as x approaches infinity. So what's going on with our function? Well, notice that this term right here is going to take over in the numerator. So as x gets larger and larger, this 3x to the fourth takes over in the numerator, and this 5x squared takes over in the denominator. So we end up getting 3x to the fourth over 5x squared, which then we can cancel and get 3/5 x squared. So that would be considered the right in-behavior model. So to figure out a left in-behavior model, you think about what happens as x approaches negative infinity. Well, because it's negative, I'm raising something to the fourth power, and I have here to the second power, so my value is still going to be positive. So I actually get the same thing. So my in-behavior model, my right in-behavior model, and my left in-behavior model are the same. Okay, so here's another one. We're going to find an in-behavior model for this function f of x equals x plus e to the minus x. So again, we're going to think about what happens as x goes to infinity. So as x gets really large, so think about, so this is getting larger, but think about what's happening here. X is positive because it's approaching positive infinity. So remember, we can think of e to the negative x as 1 over e to the x. So as x approaches infinity or gets larger and larger, this value right here goes to 0. So that fraction goes to 0. So as x approaches infinity, f of x starts to take on this shape, and it's going to look linear. So x would be my in-behavior model. So that would be for the right end behavior model. And sometimes they'll call, we're going to see a formula in just a minute, where they'll call that like g of x for our right end behavior model. So what about a left end behavior model? So think about what happens as x approaches negative infinity. So now this is going to become, it's going to stay negative, and it's going to get smaller and smaller. So then what happens to e to the minus x? So if x is negative this time, now I'm taking the opposite of a negative. So this is going to be a positive exponent. So when x is approaching negative infinity, this is going to explode, because that's going to get huge. So that takes over. So our left end behavior model, I'm going to call g of x, is going to be e to the minus x, because that function is going to take over. So we have this fancy formula for in-behavior models. It says they model the behavior of a function as x approaches infinity or negative infinity. So notice I didn't really use limits, even though I used that limit idea, but I didn't really use the limit notation when I was just describing that. But here we do use it when we are showing a proof here. So a function g is a right in-behavior model for f if and only if, here's some trivia for you. If you see this in a math textbook, that means if and only if, and that is used in mathematical theorems and proofs. It goes both ways. So when you see if and only if, that means, you know, if then, and it goes the reverse way as well. So we're looking at the limit as x approaches infinity of f of x over g of x has to be 1, which remember g of x is the in-behavior model. And a left in-behavior model for f, that function g would be a left-hand behavior model for f if and only if that limit as x approaches negative infinity of your function over your in-behavior model equals 1. So let me show you this with the one we just did. So the right in-behavior model we said for g of x was x. So then to use this, to show this mathematically as a proof, I would look at the limit as x approaches infinity of f of x over g of x, so that's x plus e to the minus x over x. And I need to show that this equals 1. Okay, well, I'm going to break this apart as x over x plus e to the minus x over x. All right, so then x over x is just 1. And then we have e to the minus x over x. Okay, so let's think about what happens as x is getting larger. That means, remember, we can think of this. I'm going to write down one more step. We can think of this as, I just flipped this to the denominator since it was a negative exponent. X is getting larger. That means that this is going to 0, which means we get 1, which is what we were supposed to get. So we just showed that x is a right-end behavior model for f of x. Okay, so then let's show this next one. So to show the left-end behavior model, to show that it's equal to that, we're going to look at the limit as x approaches negative infinity of f of x over g of x. We need to show that that equals 1. So I'm going to split it apart. So I'm going to have x over e to the minus x plus e to the minus x over e to the minus x. And I know you guys know I couldn't do that if it was the other way around, but it's over a common denominator, so I can split the fraction apart. So this just reduces to 1. I guess I should probably have parentheses there. So we have the limit as x approaches negative infinity of, I'm going to leave it like this. Okay, so now let's think about what's happening here. If x is negative and getting smaller and smaller in the negative direction, that means I have the opposite of a negative. So that means that this in the denominator is getting huge. So this takes over, which means this goes to 0 and I get 1 for my limit. So then that is proving both sides, the right-end behavior model and the left-end behavior model. So I just wanted to kind of quickly go over that. I think on your review for limits, we have a question similar to this, so I wanted to make sure that I showed you how to do this.